Hello and welcome to Statics Time. Today we have these three gentlemen on, and they're going to talk to us a little bit about building a water tower in Adre village in Chad in Africa. Let's start with my name. I'm Enzo.
I'm Will.
I'm Jeremy. And I'm Caden.
Nice. We're building a water tower in Adre village in Chad because it has a lot of problems and they need water. It's located in eastern Chad near the Sudanese border, and it has a major influx of Sudanese refugees since the Civil War in 2023. There's some combined pressures there, including drought and desertification from the Sahara expanding. All this conflict-driven displacement, combined with weak infrastructure, means that people in Adre village don't have access to the water that they need. And I'd like to have Jeremy tell us a little bit about why that is a problem.
Yeah, I'm glad you bring that up. So the problem with unsafe drinking water, there's a couple reasons that this is the case in this area. So the water availability is around 5 to 6 liters per person, which is a lot less than what an average adult should have, which is around 15 to 20 liters. Having unclean drinking water as your main source of hydration leads to cholera outbreaks, which will spread fast among a small village. And then this leads families to prioritize things like finding safe water over their hygiene, which is not a sacrifice you can be making. And then the cycle of poverty in these areas lead to them not being able to find other sources of water and just being stuck in the same loops over and over again.
Man, that's a shame. Caden, can you tell us how the Christian worldview applies to this situation?
Yeah, God tells us as Christians to take care of the poor and those who are less fortunate than us. So we have a moral responsibility, not just an engineering problem here. In Matthew 25:35, it tells us, "I was thirsty and you gave me something to drink." So that's basically what we're basing our project off of here. We're going to give the people of Adre village water to drink because they're thirsty and they don't have anything to drink that's clean. So we're going to go there and give them what they need.
All right, wonderful. Let's hear a little bit from Will about some possible solutions to these issues in Adre village in Chad in Africa.
I'm glad you bring that up. There are a lot of avenues that we could have taken. There's water treatment facilities, import supply lines, water diversion projects, water reclamation, rainwater harvesting, aquifer wells, water infrastructure repair, but we landed on water towers. So Adre village isn't really near any major bodies of water that we could divert with dams. They don't get consistent rain, so rain harvesting doesn't really work there. Aquifers must be present to drill wells, and they don't have that. So really the best route that we thought we could take is importing, whether it's importing water itself or importing filters to filter out the water, and then in addition to that, building a water tower so that they could store it cleanly.
Good thinking, Will. What were some of your different variations of water tower designs that you considered during this project?
So we came up with a design A on the right and a design B on the left, and then as you can see there's the 2D and the 3D modeling. So we chose 316 stainless 4-inch square quarter-inch tubing to make our water tower. Extremely durable material in an extremely hostile environment. The designs themselves are simple and easy to manufacture in such a honestly hostile and impoverished area. And then we wanted everything to be easy to transport, easy to get to the area, so nothing that they can't get a hold of.
And what kind of constraints did you have on your design as far as what it needed to withstand?
So we wanted to carry 200 gallons of water, and we wanted this to be able to withstand double the wind speed for that area.
Great, sounds good. Well, Jeremy, talk a little bit about the kind of calculations that you performed to get this thing ready to go.
So once we had the design, and put it down on paper, it was statics time. It was go time. It was just another problem. The method for this specific truss or these two designs was method of joints was the preferred method, just to solve it in each section and then calculate the force in each beam. We decided to solve it for variables initially on paper, so this is for design A and for design B. That led us to putting it into Excel and then just changing the wind force and the force from the water to give us all the forces in our beams.
Great. Well, how about you talk a little bit about the static simulations you did to see what the pressure from the water and the wind was going to do to our water tower design.
So as you can see, we got design A on the left, design B on the right. We have displacement on top, and we have stress on the bottom. So displacement is going to tell you how much that structure is going to change when those loads are applied, and then stress is going to tell you how much compression or tension is happening on any of the members at any particular point. So it's a little hard to see in the picture, but with our given loads of 200 gallons of water and double the wind speed, our structures for design A and B, they displace practically zero and they receive practically zero stress.
Wonderful. Well, Jeremy, why don't you tell us a little bit about the design we picked and why we picked it?
Yeah, so we decided to go with design B for many reasons. As you can see, our designs were very similar, except for design B had taken away that bottom member. And because they were so similar, they had similar values in the force in the beams. So because it had one less beam, that led to lower cost and easier manufacturability when it came to actually building this thing in Chad. There weren't many performance drawbacks, and the lack of a bottom beam meant that there was 16 less feet of tubing needed, which reduced the cost of the tower by around $500.
Wonderful. Well, Kane, how about you tell us a little bit about the economic factors and what we actually need to build this water tower?
Yeah, so here's our bill of materials. As you can see, it's broken down by each thing that we need, basically by price and how much we need of it. So first of all, we need the tubing to build it, obviously, as well as the metal saw so we can cut it to the specific lengths. MIG welder so we can weld the tubes together once we cut it, as well as the concrete and the footing so we can make sure it doesn't move when the wind comes and it can support what it needs to support, as well as a generator to power the tools that we need to use to either weld or cut or deburr our metal tubes before we weld them so we don't get cut, basically, as well as anchor bolts to bolt everything down. And that comes to a total of around $9,000 to build this tower.
Sweet. Well, let us know how we're going to put it together.
Yeah, so our assembly instructions are very to the point and simple. So first you're going to use the metal saw and measure and cut the tubes to size. Then you're going to grind the edges to make sure they're nice and smooth. Next you're going to weld each part together. Then you're going to dig the footings with shovels and insert the footings and pour the concrete in. And then place the truss inside those footings. And then place and bolt the tank on top of the structure and then fill it up with water. And that's our instructions.
Wow, amazing. Well, here are our references for the research that we did for this project, and thank you for tuning in to Statics Time.